created by MindSticks Foundation Trust. Hello, class, and a very warm welcome to today's explainer. I am absolutely thrilled to have you here today. You know, chemistry is kind of like solving a really beautiful logical puzzle, and today we're going to unlock some of its fundamental secrets together. We're going to master the art of balancing chemical equations and then discover the fascinating ways different substances interact with one another. So, get your notebooks ready, sit back, get focused, and let's embark on this exciting learning journey.
Looking at our agenda for today's lesson, here's what we'll be covering. First up, the need for balanced equations. Second, the 4 steps to balance. Third, combination reactions in action. And finally, decomposition reactions explained. Let's dive right in.
All right, starting with Section 1, the need for balanced equations.
Before we start shifting numbers around, take a quick moment to recall what you studied in your previous standard about matter and mass. Looking at our reactants on the left side and our products on the right side, the absolute golden rule of chemistry, thanks to the law of conservation of mass, is that the total mass of each element in the reactants must be exactly the same as the total mass of those elements in the products. I mean, you can't just create matter out of thin air, right? And you definitely can't destroy it. The atoms simply rearrange themselves. So if the atoms aren't equal on both sides, we've got what we call an unbalanced equation. And as good chemists, well, it's our job to fix that.
Moving right along to Section 2, the 4 steps to balance an equation.
We're going to use a highly effective trial and error method to solve an unbalanced equation. Here is your high-level roadmap. Step 1 is simply to write down the chemical equation from the word equation. Step 2 is where we put on our detective hats and compare the number of atoms on both sides. Step 3 is the heavy lifting. We balance the compound with the maximum atoms first. And finally, Step 4 is writing down the final balanced equation. To see this in action, we are going to balance the reaction between sodium hydroxide and sulfuric acid. Let's see how this builds up.
Now, let's look clearly at the imbalance here. We've completed Step 1 by writing it out. NaOH plus H2SO4 yields Na2SO4 plus H2O. For Step 2, look closely at how we're comparing the reactants on the left and the products on the right. Notice how the sodium, or Na atoms, are just 1 on the left but 2 on the right. And look at the hydrogen, or H atoms. We have 3 on the left but only 2 on the right. Oxygen and sulfur happen to be equal right now, but because sodium and hydrogen are mismatched, this entire equation is completely unbalanced.
So let's tackle Step 3. It's always super convenient to start balancing from the compound containing the maximum number of atoms. Here, Na2SO4 and H2SO4 both have 7 atoms. Let's pick Na2SO4, and specifically the element sodium. To balance the 2 sodium atoms on the product side, we obviously need 2 on the reactant side. But remember this absolutely crucial rule, okay? We cannot change the chemical formula itself. We can't just write Na2OH. No way. Instead, we apply a factor of 2 to the entire NaOH molecule. So we get 2 NaOH. Now, check it out. Sodium is successfully balanced at 2 and 2. However, we aren't quite done yet. By putting that 2 in front of NaOH, we actually changed the number of oxygen and hydrogen atoms. If we check again, oxygen and hydrogen are now unequal on the 2 sides. We need a smaller factor to fix the hydrogen. On the left side, we now have 4 hydrogen atoms in total. On the right side, in H2O, we only have 2. So what do? We apply a factor of 2 to the product H2O. The equation now becomes 2NaOH plus H2SO4 yields Na2SO4 plus 2H2O. And just like that, our hydrogen is perfectly balanced at 4 versus 4.
And this brilliantly brings us to Step 4. We do one final check of all the elements. Let's see. Sodium is 2 on both sides. Oxygen is 6 on both sides. Hydrogen is 4 on both sides. Sulfur is 1 on both sides. Everything is perfectly equal. We've officially converted an unbalanced equation into a balanced one just by applying the proper factors to the appropriate reactants and products. Our trial and error method is a complete success.
All right, let's jump straight into Section 3, combination reactions in action.
Excellent work on the math class. Now that we've mastered that, let's categorize these reactions. During chemical reactions, old bonds break and new bonds form to convert reactants into products. Now, a combination reaction is exactly what it sounds like. It's when 2 or more reactants combine in a reaction to form a single product. I really want you to heavily emphasize the phrase single product in your notes. That is your biggest clue. Multiple things go in, but only one unified thing comes out.
Let's look at 3 classic laboratory examples of this. First, ammonia gas reacting with hydrogen chloride gas.
They immediately condense at room temperature to form a solid salt, ammonium chloride, which literally looks like a beautiful white smoke. Second, when you burn a magnesium strip in the air, it combines with oxygen to leave behind a white powder, magnesium oxide. Third, adding water to slake lime, or calcium oxide, generates a huge amount of heat and yields calcium hydroxide. Now I want you to use your brain power here, students. Look at these 3 examples. In every single one, despite having multiple reactants going in, how many products are formed? Exactly 1. And that, my friends, is the absolute hallmark of a combination reaction.
And finally, Section 4, Decomposition Reactions Explained.
So if combination is bringing things together, what do you think decomposition is? Let's formally define it. A decomposition reaction is the reaction in which there is only one reactant giving rise to 2 or more products. It is the literal breaking down or dividing of a complex substance into simpler parts. Basically, one thing goes in and multiple things come out, the exact opposite of what we just learned.
Let's look at a typical laboratory setup for this. Say we take some powdered calcium carbonate in a test tube and heat it strongly with a Bunsen burner. That intense heat forces the single reactant, the calcium carbonate, to decompose. It breaks apart into calcium oxide powder, which stays right there in the tube, and carbon dioxide gas, which travels through the bent tube. And how do we know for sure it's carbon dioxide? Because when it bubbles into the freshly prepared lime water in the second test tube, it instantly turns the lime water milky. So we have one reactant dividing into 2 products.
But decomposition doesn't just happen with calcium carbonate. Look at these other really fascinating examples. If you heat sugar strongly in an evaporating dish, that single reactant sugar divides into black carbon and water. But here's the thing, decomposition doesn't always need fire. Hydrogen peroxide naturally undergoes a slow decomposition into water and oxygen all on its own. And, as you might recall from your previous standards, we can even force water to decompose into hydrogen and oxygen gases just by passing an electric current through it. This specific decomposition by electrical energy is known as electrolysis. So you see, heat, nature, and electricity can all trigger decomposition.
Now let's step away from the test tubes for a minute and connect this chalkboard lesson to the real world around us. Because decomposition is absolutely vital for life on Earth. Many degradation processes take place in nature continually. When organic waste falls to the ground, microorganisms actually break it down. They use decomposition reactions to transform that single mass of waste into incredibly useful products, like nutrient-rich manure for our soil and biogas, which we can use as a fantastic environmentally friendly fuel. See, chemistry is literally everywhere.
And that brings us to the end of today's explainer class. We've learned how to meticulously balance equations using trial and error, and we've discovered the defining differences between combination and decomposition reactions. But before I let you go, I want to leave you with a little thought-provoking question for your homework. What chemical reactions are happening around you right now? Take a look in your kitchen, look out in your garden, or even look at the rust on an old iron gate. See if you can spot chemistry in action in your daily life. Thank you so much for joining me today. Keep practicing those balance equations, and I will see you in the next class.